Good morning to all of us gathered here. I am very glad to welcome the gathering. Most respected chairman, principal, management. I am very glad to welcome the resource person of today, Dr. SASMITA, Professor of Physical Chemistry, Annamalai University. Welcome, ma'am. And I welcome all the participants, particularly YouTube participants. Now I hand over the time to Dr. SASMITA. Please, ma'am.
Thank you. Thank you, Dr. Sultan Ahmed. So I'll
Thank
start
you,
the
ma'am.
session.
Yes, ma'am.
Why it is not responding?
It will take some time, ma'am.
Okay.
After sharing the screen,
Mm.
you have to touch within the screen.
Yes, I have done already.
Then share.
Yeah.
Now it's okay, ma'am. You can start, ma'am. This is ma'am.
Minimizing option.
Minimize. Top is there, ma'am. Start presentation.
Yeah. I am audible and visible. I mean,
Yes,
the
ma'am.
screen is audible,
Yes, ma'am.
visible.
Yes, ma'am.
Okay, okay.
Yes, madam.
Thank you. I'm going to start.
Yes, ma'am. Welcome,
So,
ma'am.
I am going to start today's session. It's on
Presentation, ma'am.
photochemistry.
Full screen. Excuse, ma'am.
Pardon?
Full screen, ma'am. Full screen presentation, ma'am. Full
Okay,
screen
yes.
presentation, ma'am.
Oh, sorry.
Slideshow.
Yes. I'm sorry. Slideshow.
Fifth option at top.
No, where is it?
Slideshow fifth option, ma'am.
Yes. Yeah.
Okay, ma'am.
Is it okay?
Now leaving. Yes, ma'am. You can press. Start
Okay,
over, ma'am.
Yeah.
Thank you, ma'am.
Today we are going to start photochemistry. This is an important topic in physical chemistry syllabus of MSc students. So I will go into the basics of photochemistry and few applications thereon. So the study of chemical reactions which are caused by absorption light radiations or photons is called as photochemistry. The light radiations of visible and UV regions lying between 800 to 200 nanometer wavelength bring about such reactions. The related photons should be of sufficient energy given by h nu to raise the atom or molecule from ground electronic state to an excited state, which involves promotion of electrons from a bonding molecular orbital to a antibonding molecular orbital. In the excited state, the atom or molecule is likely to undergo chemical reaction than when present in a ground state. In ordinary thermal reactions, the activation energy results from the random intermolecular collisions. This is the thermal reaction where there is random intermolecular reaction and there is excitation of the molecules. In photochemical reactions, however, the activation energy is acquired by uh, absorption of photons of light associated with a particular amount of energy. By using a monochromatic light of a particular wavelength in the visible or UV region, it is possible to excite a particular atom or molecule in a reaction mixture instantaneously to an excited state. Thus, in a photochemical reaction, the selectivity is possible, which is not possible in a thermal reaction. So basically, the difference between the two is that this is caused by the intermolecular collision, and photochemical reactions are caused by absorption of photon. Here, all the molecules are excited after getting heat. There is a small correction here. This should be heated, and all the molecules will be excited or promoted. And in this case, only selective molecules will be excited according to our choice. So, one fine example is a mixture of hydrogen and bromine gas. I have represented black dots for hydrogen and the red dots for bromine gas. In a thermal reaction, when it is heated, all hydrogen and bromine are excited, whereas in photochemical reaction, when we give this same mixture of hydrogen and bromine to an radiation of 450 to 550 nanometer, only the bromine molecules will be excited, not the hydrogen molecules. So this is the speciality of photochemical reaction compared to the thermal reactions. Now we come to the photophysical process, which is a little different one from the thermal reaction. So here we have different terminologies to be described. We will go for them one by one. So in the introduction, I would say that it is this process, photophysical process, is that where when light is absorbed by a system, it can bring about a photochemical change. The absorption of light may result in a number of phenomena like uh, like light absorbed can cause an lowering in intensity of the incident radiation. Number two, the observed radiation may be re-emitted by different steps. So we will discuss all the processes one by one. First, we come to fluorescence. The emission of fluorescence is that when the light which is absorbed is re-emitted instantaneously and in one or more steps. And the emission of fluorescence ceases with the removal of the source light. But sometimes the light absorbed is given out slowly, and even after removal of the source light, the emission goes on. Such an example is that of a phosphorescence. All these things are well explained in our diagram called Jablonski diagram. We have to learn few more terminologies in this regard. First is spin multiplicity. What is spin multiplicity? Most molecules have even number of electrons, and thus in ground state all the electrons are spin paired. The quantity 2s plus 1, where s is the total electron spin, is known as spin multiplicity. So when these spins are paired, the upward orientation of electron spin is cancelled by downward orientation, so that S is equal to 0. Now we have another formula called spin multiplicity, total spin. So that formula is 2s plus 1. And we write this 2s plus 1 is equal to 1 when um, saying when we have S is equal to 0. So when both the electrons are of different spin, we can say that S is equal to 0 gives rise to 2s plus 1 is equal to 1, which means that the spin multiplicity is equal to 1, and we call that particular state as singlet state. Coming to when the absorption of light, when no, in which one of the paired electron goes to the higher electronic state, and the spin orientation of two single electrons may be either parallel both or antiparallel both. So in that case, the spin multiplicity, the total spin S will be equal to half plus half is equal to 1, or minus half becomes equal to 1. In that case, minus 1. So in that case, the total spin will be, or the spin multiplicity will be 3. 2s plus 1 is equal to 3. So we can say that the molecule is now present in a triplet state. So from this spin multiplicity, orientation of the spin of the electron, we assign whether the molecule is present in a singlet state or triplet state. Now, out of these two, again, quantum mechanically, it has been found that a singlet excited state has always greater energy, higher energy than the corresponding triplet excited state. For example, S1, if S1 is the first singlet state, excited state, and T1 is the first triplet excited state, then S1 energy will be definitely higher or highly placed compared to the T1 state. Now we come to the fundamentals of the Jablonski diagram. On absorption of light photon, the electron of the absorbing molecule, now I say that A0 is my absorbing molecule. It takes up h nu amount of energy and it goes to the excited state of A star. Here it is said to be in an activated state of high energy. So this high energy molecule at A star is likely to come down to a low energy or more stable state by different phenomenon. So all these phenomenons will be described as we go to the Jablonski diagram. So the first one is non-radiative transition. Second one is radiative transition, and the third one is chemical transition. So we will have the discussion of all these after referring this Jablonski diagram. In the non-radiative, as we see, we have the molecule present in the S0 or ground state. And from this S0, we have given h nu amount of energy or absorption so that the molecule can be excited to any one of the uh, excited states. It starts from singlet excited state S1, S2, S3, S4 and up to Sn. We can have n number of such singlet excited states for the molecule. Now, after the molecule is present in the highest occupied singlet excited state, it is having highest energy, hence least stability. So it would like to come down by some means so that it becomes more stable. For this, the first category comes now is non-radiative transition. This can occur in this way. So we have the molecule present here and it will like to come via internal conversion process to come to the lowest singlet occupied excited state. This is S1. So whatever is the state S2, S3, S4, Sn, all these excited molecules present in the excited states would like to come down to the S1 triplet excited state by some emission. This is called internal conversion. These transitions do not involve the emission of any radiation, hence they are called as non-radiative or radiation-less transitions. The energy of the activated molecule is just dissipated by um, in the form of heat through molecular collisions. So this is the process of internal conversion. So just like we have the molecule from S2, S3, S4 up to Sn coming to S1, we can also have similar internal conversion taking place from T3, T4, T5 to T1. This also can happen in IC. And because this is a very quick and energy leveling process, it is reducing energy and it is coming to a more stable state, we can say that this happens in a very short span, very quickly of the time span of 10 to the power of minus 11 seconds. Next we come to um, uh, another type. When the molecule is present in S1, it may also lose energy by another process called intersystem crossing or ISC. By intersystem crossing, it travels from S1 to T1. And as we know, this is singlet state and this is triplet state, and from here to here there is inhibition or there is change in the spin of the molecule, hence this is spectroscopically forbidden, hence the rate is very very slow. But in our previous thing I have told that both IC internal conversion and ISC, the intersystem crossing, both are non-radiative transitions. Coming to the radiative transitions, these transitions involve the return of the activated molecule from the S1 level or T1 level to come down by some means. Let us see how it happens. These transitions, when it is coming from S1 to S0, these transitions are accompanied by emission of radiations. And as we know, from S1 to S0, this is same spin transition. Hence, it is an allowed transition. And this is, the name is that of fluorescence. And it takes place at about 10 to the power of minus 8 seconds. And then suppose via ISC, the molecule has now been placed in T1, and from T1 it wants to come down to the S0 level. Again, from T1 to S0, there is a spin change. Hence, this is again spectroscopically forbidden. Hence, it takes place very slowly, of the order of maybe 10 to the power of minus 3 seconds. So you can see how fast fluorescence is occurring and how slow phosphorescence is occurring. So this what happens here is the lifetime, the emission of radiation or the lifetime of the fluorescence are much longer since the transition involves spin inversion, which needs some time for its occurrence. But whatever may be the case of either fluorescence or phosphorescence, both come in the category of radiative transitions. Radiative transitions. The first one was non-radiative transition. Now it is a with radiation it is happening. So radiative transitions. So these two transitions can happen to bring the molecule back to the ground state where it is having low energy and hence more stable. As we know, in all the chemical reactions, they will always have a tendency to come to a low energy state, which is more stable for them. So they will be very much comfortable. The molecule will be comfortable in a low energy state. Next, we come to the last type of transition, which is chemical transition. Uh, the activated molecule may lose energy by undergoing chemical reaction. Since the molecule in the singlet state returns quickly to the ground state very quickly, it gets no chance to react chemically. But when the molecule in a triplet excited state is returns to the ground state comparatively slowly, it finds ample time to react, to undergo any chemical reaction on the way. So you can say that the molecule which undergoes chemical reaction, we can say that molecule was most probably present in the triplet excited state earlier. So this is a prediction which can be made. Next, when the molecules are coming to we will describe the entire process of photochemical reaction in dividing it into two different processes. First is primary process in photochemical reaction, in which the reaction is initiated, and another process named secondary process where the reaction is continued in a chain direction, chain like manner, and again it finds a termination at the end. So we will discuss the primary process first. Let us see how it happens. The first step in photochemical process is we have the absorption of light energy. An atom or molecule with H nu absorption in the range of 200 to 800 nanometer goes to the excited, makes the atom excited or activated, and after that it goes to the photochemical product. So it gives rise to the excited atom or excited molecule, and the excess energy gained by the molecule may be transferred to other molecules by collision, resulting into kinetic energy. And now the electronic energy transition, which occurs on absorption of energies, is accompanied with changes in vibrational and rotational quantum levels, and this is governed by Frank-Condon principle. When this is governed by Frank-Condon principle, we can have four different processes or conditions in which it can occur. The first case is that, and in all these four cases, 1, 2, 3, and 4, on the x-axis, we have taken intermolecular distance, and in the y-axis, there is potential energy. For all the cases, it has been run in that manner. And out of these two each curves, the first one is standing for the ground state level, and the second one for the excited state level. When the atom is present in ground state in all this, and the atom is excited to this the higher energy level. In the first case, let us see what happens. We have the molecule in the ground state. The molecule has to uh, acquire h nu amount of photon or energy and get transferred or get excited to the higher vibrational state. When it goes, the molecule to a higher electronic state, it will assume a definite vibrational level, a particular vibrational level as it has been shown here. In the first case, the upper electronic, the upper intermolecular distance, this upper intermolecular distance is little higher than that in the ground state. In such case, what happens is there is no direct dissociation of the molecules, and the structure of the electronic band of the molecules will be appearing in this manner, fine structure. The spectra will appear like a fine structure. So, if the first case is that the intermolecular distance in the excited state is little higher than the ground state. Now coming to the second one. In this case, the molecule from the ground state is raised to a higher electronic level, acquiring quantum level, which is just above the stability level. That is, E is slightly greater than EB. EB is the binding energy. So the binding energy is that energy which binds the molecules together. So any energy little greater than that also will have a tendency to break the molecules apart to its atoms, radicals, or whatever. So the molecule, when it reaches the excited state, and as these are all vibrational levels, molecule on its first vibration itself will undergo dissociation. Up to that level, when we reach up to this level, we have 1, 2, 3. So these two levels, there will be quite a little bit of stability, as in this case, previous case. So those cases will come as fine structure in the spectra, whereas when it comes to this level where it is going to be dissociated immediately, this is given by a continuum. So this appears like a continuum in the spectra. Coming to the third type. In the third type, and in this case, what happens is the absorption of the energy may raise the molecule to an electronic state which is already in an unstable state. That is, energy is very much higher compared to the EB. That is why this particular upper level does not show a minimum, just like in the previous cases. There is no minima in the at the curve of the curve. So when the photon is absorbed here, immediately it breaks into atoms or radicals. So there is only a continuum visible for this kind of spectra. Coming to the fourth category. Here, the absorption of light by a molecule may be raised to a stable higher electronic state. As you see, I have drawn, there are two excited energy levels, vibrational levels. So I have named it as 2 and 3. These 2 and 3 are energetically very close to each other. Only difference is that 2 is a little bit stable and 3 is little bit unstable. So you can predict that from the diagram that has been drawn in this manner. So the molecule is absorbed to a higher electronic state, and from here it intersects with it, and it immediately molecule in the excited state shifts from stable 2 to unstable 3 curve. So after this shift, the molecule dissociates to give atoms or radicals. And this particular phenomenon is named as pre-dissociation of molecules. And when we look at the spectra of this kind of phenomenon, we first come across a fine spectrum appearing in the beginning. Then there is a continuum because of the dissociation. And again, we may also find a little bit of fine spectra following the continuum. So this is how all the 4 cases we have seen the state of the affair for primary photophysical processes. In the primary process, the reaction is initiated and it follows this kind of 4 types of conditions where how it can initiate the reaction. Next, we come to the discussion of secondary process. Now we assume that our molecule has already completed primary process, but still we will start from this to know the entire scenario, what is happening in photochemical reaction. Secondary processes which involve excited atoms or molecules or free radicals produced in the primary stage. It takes place themselves quite independently and light radiation. It is the immediate consequence of absorption of light. As we see, we have chlorine molecule which takes up a new amount of energy to form 2 atomic chlorines, which is the primary process. Now we have produced 2 atomic chlorines now, which will undergo, which will enter into the secondary process. Let us see how it is going. One atomic chlorine goes and it combines with the molecular hydrogen to form HCl and H. Atomic hydrogen is now produced. This atomic hydrogen again takes up the chlorine molecule from the reactant and forms HCl and chlorine. So these are actually chain propagation steps of the secondary reaction. Now we have produced HCl, H and Cl from the propagation or a chain propagation of the secondary process. Now let us enter into the second level of the secondary process, where we have now 2 atomic chlorines developed here or here. They will come to combine to become the molecular chlorine, which is less reactive. And we have also the atomic hydrogens formed here in the propagation stage to get united to form uh, molecular hydrogen, and the hydrogen and chlorine together to form the molecular hydrogen chloride. So this way, all these 3 are now trying to stop the reaction by the second process of secondary process named as termination. So here the reaction stops. If the reaction, secondary process, is exothermic, then the heat of reaction may activate other molecules, thereby causing them to react. This is another reason for higher chemical product or quantum yield. Now we will come to the process of how to find the result of the chemical reaction. Before that, what happens in secondary reaction is number 1, the excited molecules get deactivated before they form products. It can be deactivated. Number 2, there is another way of dissipating the energy, that is the collisions of excited molecules with non-exciting molecules, which can cause the farmer to lose energy. Number three, the primary photochemical process can also get reversed. And the fourth one, the dissociated fragments can also, in some places, recombine to form the original molecule or the reactant molecule. In all these four cases, these are the four methods by which the energy dissipation of the photophysical reaction takes place. And since the sum of the primary quantum yield, now we will come to the result of the photochemical reaction, which is described in a term called quantum yield, phi I, for all photophysical and photochemical events. So this is a parameter which must be equal to 1, regardless of the reactions involving the excited state. So we can summarize, or we can sum up all the phi I factors to be equal to 1. It follows that for an excited state, decay in the ground state happens only via the photophysical processes described in Jablonski diagram. So we can say that in the Jablonski diagram, we have described a process named fluorescence, phosphorescence, IC, and ISC. And all these processes will have a fraction of its contribution towards the total quantum yield of the process. So here in Jablonski diagram, we have to mention each fraction this way. This is the phi F standing for the quantum yield for fluorescence, quantum yield for phosphorescence, quantum yield for IC, internal conversion, and quantum yield for intersystem crossing. So all the four processes give rise to the total quantum yield of the photochemical reaction, which sums up to 1. The quantum yield is also affected by the intensity of light. For instance, when radiation from a highly intense source such as laser falls on the molecule, the latter can absorb even 2 photons instead of 1 simultaneously. So now we will come to the discussion of quantum yield. What is quantum yield? It has been described in 3 different manner. It is the number of molecules absorbed to undergo chemical transformation per quantum of absorbed energy, and it depends on the light intensity. The more intense is the light, the higher is the quantum yield. So the phi we can define phi in this way, or quantum yield in this way: number of molecules reacting in a given time divided by the number of quantas absorbed in the same time. Or we can also say that the number of moles reacting by the number of Einstein absorbed. Still, another definition lies in this way: rate of photochemical reaction by number of Einstein absorbed. So the quantum efficiency is always equal to unity, or 1. But in most cases, a molecule activated photochemically initiates a series of thermal reactions called secondary reactions. Under such condition, there will be 1:1 relationship between the number of quanta absorbed and the number of reacting molecules. In some cases, a molecule activated photochemically undergoes deactivation of its own. In that case, the quantum yield becomes less than 1. But in certain secondary chemical reactions, the activated molecules will go in a chain reaction, and they produce much more number of active molecules or radicals on the way, making the secondary process very, very high, more than 10 to the power of 3 or 4 order. So the secondary process can have invariably always the primary quantum yield is either less than or equal to 1, but the secondary process quantum yield is always greater than or equal to 1. But when there is there is a generation of high temperature, or there is some extraordinary experimental condition, or the reactivity of the chemicals, we can have even the secondary process quantum yield to be 10 to the power of 4 or 6 order, very much high compared to 1. Now, we have to next think of how much chemical reaction has taken place, photochemical reaction has taken place, and how to measure the yield of such a reaction. Well, the yield, the quantum yield, can be measured by some method to know the extent of the photochemical reaction. So, for such purpose, actinometers are used, chemical actinometers. A chemical actinometer is actinometers are used to measure the intensity of light radiation. So a chemical actinometer generally consists of a gas mixture or solution which are sensitive to light. When radiation fall upon these substances, a chemical reaction will take place, and the extent of which is a direct measure of energy absorbed. There are two different types of actinometers normally are in use. One is uranyl oxalate actinometer. This uranyl oxalate actinometer works in this way. It consists of a dilute solution of oxalic acid with uranyl sulfate. And uranyl sulfate serves as the to sensitize the decomposition of oxalic acid. On exposure to UV radiation, which falls on the range of 250 to 450 nanometer, the chemical reaction, photochemical reaction takes place, and the oxalic acid is therefore decomposed to carbon dioxide, carbon monoxide, and water. And this uranyl sulfate oxide is remaining as such untouched without any reaction. The extent of the decomposition of oxalic acid is a measure of intensity of light absorbed. The progress of the reaction is determined by titrating the oxalic acid with the potassium permanganate before and after the exposure to light. And from this, it can be determined that the amount of decomposition is directly proportional to the intensity of light as well as the time of exposure. There is yet another type of actinometer named Eder's actinometer, which was followed based on this principle. The system has been exposed to radiations, and the mercurous chloride is taken with ammonium oxalate, and this acts as a sensitizer, and the ammonium oxalate comes to decomposes to ammonium chloride. And the mercurous chloride is formed from the mercuric chloride, and the change in the mercurous chloride composition or weight of the mercurous chloride before and after the reaction, or the carbon dioxide evolved in during the reaction, can be determined, which can be used for calculating how much of these reactants have been consumed under in what extent of time, so that the radiation can be measured according to the photochemical reaction taking place. So these are the two different types of actinometers used for calculating the yield, quantum yield, or the photochemical yield that has taken place during the primary and secondary photochemical reactions. There are numerous applications of photochemistry. They are a boon to today's mankind. We will discuss only important 5 or 6 among them. So let us start with photosensitization. Certain reactions are known which are not sensitive to light. These reactions can be made sensitive by adding a small amount of third substance which can absorb light and transfer energy to the reactant. This third substance, which itself does not undergo any change, are called photosensitizers. So this role of the photosensitizers is almost the same as that of a catalyst acting in a chemical reaction. It can only promote the reaction, remain silent in the process of chemical reaction. Photosensitized reactions are spontaneous, involving an increase in free energy of the system. So this is the photosensitization which has been described here. In the case of photosensitizer, we have two things. One is a donor, the other is an acceptor. We have the ground state, triplet state, and singlet state of the donor as well as that of the acceptor. The acceptor's energy levels are the excited state of the acceptor are little lower compared to that of the donor. Now to begin with, we have the donor molecule having the excited, and then it is promoted with h nu amount of photons, which falls on the photosensitizer. The photosensitizer is now excited, and the excited state of the photosensitizer helps the acceptor molecule, the normal acceptor molecule without any energy, converts it to the activated molecule of the acceptor, and in the process, the sensitized photosensitizer with activation, it comes down to the normal photosensitizer molecule after passing on the extra energy from the photosensitizer to the acceptor, and this gives rise to the product. Now here what happens, we have the molecule here in the donor ground state. With h nu amount of energy, it goes to the S1 state or singlet state of the donor, and via ISC, intersystem crossing, it comes to the more stable state of the triplet, that is T1 state. So this is described as D1 and D3 for the donor, triplet and singlet state respectively. So after coming here, it to the triplet state, which is having lower energy compared to the singlet excited state, the molecule needs to come down for lowering its energy and increasing its stability. But while coming down, a part of the energy has been pumped off to the acceptor molecule, and which helps the acceptor molecule to go to the T1 stage, that is the triplet state of the acceptor. So now when A3 gives rise to the product, we say that photosensitization has taken place. A numerous photosensitizers are used nowadays. Some examples of atomic sensitizers are mercury, cadmium, and zinc. And some molecular sensitizers are to be noted, which are benzophenone and sulfur dioxide. It should be remembered here that the photosensitizer act as a carrier of energy. So this carrier of energy sensitizes another molecule which is not otherwise having any photosensitivity activity and makes it photosensitized, and the photosensitizer comes back to the ground state after passing on the energy to the donor or the reactant molecule. Next we come to laser. All of us are very familiar with the activity of laser in um, our day-to-day activity. Uh, Laser is nothing but light amplified stimulates emission of radiation. Let us discuss how laser action takes place. The spontaneous emission is a random process obeying the unimolecular rate law, and the emitted radiation is incoherent. The divergence of radiation in all directions causes loss of light intensity on propagation. So the incoherent beam cannot be taken to be very intense manner in any of the directions because they lose their intensity by this. But if a beam of light radiation is generated with all the photons making it vibrated in the same phase, then the energy of radiation is localized in a small angle. The intensity of radiation is preserved even on propagation to long distance. This property of stimulated radiation is of immense use in laser technology. Radiation from laser source happens in this way. For electronic uh, energy states at ordinary temperature, only the ground state is populated. Only the ground state is populated. When a stream of photons allowed to impinge on such a system, absorption is preferred, and the molecule in the excited state now starts getting built up to the initial state by emitting radiation. The photon till such time that, and sometimes there is a photostationary equilibrium established. If by some means the population of the excited state can be increased on the impinging photon is more likely to encounter an excited particle. So when we impinge one excited molecule compared to a normal molecule, there is possibility of there is possibility that on each photon impinging on the system, an extra photon is added to the beam, and under these circumstances the emitted intensity will be larger than the incident intensity. This is known as laser action. The radiation which promotes the molecules to the upper state is known as pump radiation. One requirement for laser action is that in between the ground state and the excited state, there should be another state called metastable state. This metastable state is an excited state which is with a long enough lifetime for it to participate in stimulated emission. Another important requirement of laser is that existence of greater population in the metastable state. than in the lower state. It is necessary to achieve
Dear participants, sorry for interruption. Uh, there will be a break because of a network issue. Thank you for being patient. Session will be continued soon.
Everyone can see, and are you able to hear now? Dr. Sultan, are you able to hear?
Yes, madam. Participants are waiting. You can continue over, ma'am.
Okay. Is it visible now?
Yes, ma'am. Yes, ma'am.
Okay.
Now, ma'am, presentation slideshow.
Yes. Sorry. I will discuss last 4 slides.
Yes, ma'am.
Okay. So we will discuss laser. This was already
Already we have
completed.
Yes, ma'am.
Completed.
Yes, ma'am. Yes, ma'am.
Okay.
At the end, we
Okay.
have discussed about classes.
Okay. No. Photosynthesis.
No, semiconductor not yet, ma'am.
No. Photosynthesis completed.
No, madam.
No. Photosynthesis. I will start from photosynthesis.
Yes, sure, ma'am. Sure, ma'am.
Okay. Another 10 minutes.
Okay, ma'am.
Okay. Continue. The energy which supports the activities of most living organisms on the earth is derived directly or indirectly from the energy of sunlight through photosynthesis. This is a process in which simple carbohydrates are synthesized, form water and carbon dioxide in the chlorophyll containing tissues of plants in the presence of sunlight. Oxygen, being a byproduct, is given out. The released oxygen, which comes from the photosynthesis process, comes from water, not from the carbon dioxide. And this was verified by a group of scientists taking O18 isotope of water in O18 isotope of oxygen in water, and this was detected in the oxygen, which came out as a byproduct. The photosynthetic products are energy-rich organic compounds. The potential chemical energy of these compounds comes from the light energy. The light energy, to be effective in photosynthesis, must be absorbed by a suitable pigment. The vital role is performed by the green pigment chlorophyll in plants. Now coming to little bit detail of chlorophyll. There are 7 types of chlorophylls available. Chlorophyll A, B, C, D, E, bacteriochlorophyll, and bacterioberidin. All these chlorophyll molecules contain a tetrapyrrole skeleton formed in a ring with an atom of magnesium in the center of the ring. A so-called pyrrole molecule contains a skeleton of 5 atoms. 4 carbon and 1 nitrogen, and 5 are arranged in a ring. And 4 such pyrrole molecules are arranged in a ring, which form the head part of the chlorophyll molecule. And in the tail part, we have an alcohol like phytol, which are a long chain of linked hydrocarbons. Now, coming to the path of carbon dioxide in photosynthesis. Air contains 0.03% carbon dioxide. This gas diffuses into air spaces between the cells of the mesophyll of the leaf through open stomata. Here it combines with water to form carbonic acid. Transportation of carbon dioxide in the form of carbonic acid takes place from spongy cells to the palisade cells of the plant until the main site of the photosynthesis is reached. It is now proved that photosynthesis, carbon dioxide is not reduced as such, but first it forms a complex with the cellular compounds, and then it is reduced by some activated compounds produced as a result of the photochemical reaction. There have been many evidences that the photosynthesis consists of two phases. One is dark phase, the other is light phase. The reaction of the light phase is light sensitive, and therefore it is called as a photochemical reaction. The reactions of the dark phase do not require light, but they are temperature sensitive. And such reactions are called Blackman reactions. There are two different type of phenomenon occurring in the dark phase and light phase. We will briefly go into those details. A group of scientists found that the rate of photosynthesis was less when compared with uh, uh, light in continuous illumination or alternatively to light and dark cycles. The increase in the rate of photosynthesis was enhanced greatly if the span of light period was reduced. This is because the light period followed by the dark period allows the cells to utilize all the products of the light reaction by darkness allows the cells to the reduction of carbon dioxide in the dark reaction. Temperature experiments. When the photosynthesis is carried out in excess of carbon dioxide, but in the presence of low light intensity, the rate of photosynthesis does not increase with increase in temperature. This indicates that some reaction requires light and is not affected by rise in temperature. When the concentration of carbon dioxide is low and the intensity of light is high, the rate of photosynthesis becomes double for every 10-degree rise in temperature. This shows that there must be a reaction which is not affected by light. So it has been proved almost mm, it has almost been proved that the alternate cycle of dark phase and light phase gives the maximum yield to the photosynthesis process. Coming to semiconductor photocatalysis. In heterogeneous photocatalysis, semiconductors act as photocatalysts in the photomineralization due to their specific electronic structure, which is characterized by a filled valence band and an empty conduction band. Uh, there are many semiconducting materials available. when a semiconductor is illuminated by UV light, one electron here is this is a h nu amount of energy. One electron is excited from valence band to the conduction band, creating a hole in the valence band. Now we have one electron in the conduction band and we have a hole in the valence band. Hence, we have a electron and hole pair. This electron hole pair is very important in the semiconductor industry, and their concentration in a particular semiconductor matters a lot of property to the particular semiconductor material. There are many semiconducting materials which are commercially available and investigated for as photocatalysts, but only a few of them are suitable for efficiently catalyzing the photodegradation of a wide range of organic contaminant. Some examples of semiconductors are tin dioxide, titanium dioxide, zinc oxide, zinc sulfide, cadmium sulfide, iron oxide, ferric oxide, and tungstenium oxide. Out of all the semiconductors, titanium dioxide has proved to be the benchmark catalyst against which the photocatalytic activity of other semiconductors is measured. This is because of its high photocatalytic activity. Zinc oxide stands next as a suitable alternative to titanium dioxide and proved to be efficient, even more efficient than titanium dioxide in several applications. There is a minimum requirement for a semiconductor industry which has to be satisfied. In the there should be a suitable electron hole scavenger, and the photo-generated electron hole pairs may recombine and dissipate the input energy as heat within a few nanoseconds. Hence, for a photocatalytic process to be efficient, electron must be promptly removed by an electron acceptor the moment it has been excited from the valence band. So the electron acceptors are necessary for photocatalytic process. The photo-generated due to the high oxidation potential, the semiconductors can oxidize most of the inorganic species in wastewater into carbon dioxide and their mineral acids. Hence, a very important application of the semiconductor photocatalysis is in the remediation of water pollution. Next, chemiluminescence. This is used in the biological field. Chemiluminescence is applied in forensic labs by scientists to solve crimes. Here they use luminol and hydrogen peroxide. The iron which is present in the blood acts as a catalyst and reacts with the luminol and hydrogen peroxide to produce blue light for about 30 seconds. Thus, it helps in the forensic lab scientists to invest in the investigation. So, thank you for patient hearing.
Thank you, ma'am. Very interesting session. Thank you so much. And one of the participants commented like this, ma'am. Photosynthesis is tricky topic, but you are explained neatly like that. He chatted, ma'am. He commented.
Thank you very much.
And myself also, I'm very happy to know that, ma'am. Previously, myself too, I have taught 2 types of photosynthesis, only green and yellow pigment. And now only I let to know the 7 types of photosynthesis. Sorry, yes, photosynthesis. That also very
Chlorophyll.
interesting too. Yes, ma'am. Yes, ma'am. Chlorophyll. Yes. Chlorophyll.
No, I did not. I gave a brief idea about chlorophyll because I did not go
Yes,
into
ma'am.
the
Yes, ma'am.
details of.
Yes, ma'am. Very
Yeah.
interesting and useful too, ma'am. Both the days are very useful. Thank you so much.
Thank you.
And
Thank you very much.
yes, ma'am. Thank you, ma'am.
So I thank at the
Yes, ma'am.
the organizers of SHANMUGAM College of Arts and Science, Kalakurchi, for giving me this opportunity. The principal, Professor J. Ahmad Sultan, Dr.
No,
Jayasilan.
myself, I'm head of the department, ma'am.
Oh, you are head of the department. I'm sorry, sir.
Yes,
I'm
ma'am.
sorry.
It's okay, it's okay, ma'am. It's okay, ma'am.
So, Sangeeta madam, I thank all of you for inviting me.
Thank you, ma'am. Now it is time to thank ma'am. It is for vote of thanks. Now I call upon Professor Sangeeta to deliver vote of thanks. Welcome, ma'am.
Hello, Vadi Blanca.
Yes, ma'am.
Good morning to everyone. I am very glad to take this opportunity to deliver vote of thanks for this 2-week online lecture on free online competitive exam coaching for chemistry, organized by Department of Chemistry with the Internal Quality Assurance Cell of Dr. R.K. SHANMUGAM College of Arts and Science, Kallakurichi. First of all, on behalf of Department of Chemistry, I thank the management for accepting and grant permission to organize such a grand event. I thank our HOD, Dr. J. Ahmad Sultan, for welcome address. Thank you, sir. And I thank our principal and IQAC chairman, Dr. G. Moganasundar, for principal address. Thank you, sir. My sincere thank to our chairman, Dr. K. Magudumudi, sir. Dr. K. Magudumudi, sir, for valuable time spent with us, particularly COVID-19 emergency. Thank you, sir. And also thank our correspondent G.S. Kumar, sir, and Secretary Engineer N. Govindaraj, sir. Thank you, all of you, sir. My sincere thank our academic advisor, Dr. Madhivanan, sir, for felicitation address. Thank you, sir. And I would like to thank our Vice Principal, Dr. P. John Victor, for felicitation address. Thank you, sir. I am very glad to thank our resource person of the 2 days, Professor Physical Chemistry, Dr. SASMITA Das, for the excellent presentation of the surface chemistry and photochemistry. And thank you, ma'am. Today's coronavirus for a gas mask for the principle of surface chemistry. Surface chemistry உடைய பிரின்சிபலை பேஸ் பண்ணி தான் வந்து கேஸ் மாஸ்க் அப்படிங்கிற அந்த சொல்யூஷன்ஸே இருக்கு. அது இந்த மாதிரி டாபிக்ஸை செலக்ட் பண்ணதுக்கு மேம்க்கு ரொம்ப தேங்க் பண்ணிக்கிறோம். ஏன்னா இன்னைய சுச்சுவேஷன்ல ஏசிலாம் வந்து வேணாம் அப்படின்னு சொல்லும்பொழுது போட்டோ கெமிஸ்ட்ரி ஃபார் த சன்லைட் light based topics. 2 topics are in today's situation face பண்ணி இருக்கிறதுனால ரொம்ப தேங்க்யூ மேம். And I thank everyone, organizing committee, coordinators and participants. Thank you one and all. Thank you. Thank you, sir.
Thank you, ma'am. Thank you, ma'am. Thank you for vote of thanks. I thank, personally, I thank all the participants and Madam, Dr. Srilas Madam, and coordinator, Dr. Jayasilan, and everyone. Thank you, one and all. Thank you.
Thank you, sir.